Hello all. In today's session, let we learn about shift register. In last session, we learned about your buffer register, where these buffer registers are used only to store the data or to process your data using your central processing unit. So in those applications, we are going to use these buffer registers, whereas shift registers are used to shift your data from one unit to the other unit. So now in these registers, based on your how you are taking your output from your flip-flops or how you are giving the input to the register. So based on that, so in the manner of your serial or in a way of your parallel form, you're going to collect your data in the form of your serial or the form of your parallel. So it has been classified into four categories: serial in, serial out, shift register, serial in, parallel out, shift register, parallel in, serial out, shift register, parallel in, parallel out, shift registers. Now let me deal one by one. So now these are the simple block diagrams of those shift operations. The first one will give you the serial in, serial out, shift register. Second one is also belong to serial in, serial out, but the data is shifted in the direction of your rightward, hence it comes under your shift right register, serial in, serial out. Whereas the data is shifted in a leftward direction and your data input is on your extreme right and data output is collected from your left hand flip flop. So hence it comes under serial in, serial out, shift left. The data is shifted in the leftward direction from one flip flop to other flip flop. Next, but here parallel in, serial out, shift register. So now each block is treated as your one of the flip flop. So you're giving the input parallelly to all the flip flops. So upon loading the data into the register, and you can collect the data bit by bit in a serial manner. So hence it comes as your parallel and serial out. Next, serial in, parallel out. So upon loading the data serially in all the flip flops, then you can collect the data using only one clock signal. You can obtain your all the data bits. So till that, so it will be invalid state. So if it is loaded fully, then only the outputs are treated as your valid outputs. Next, parallel in, parallel out. So method of entering the data in a parallel form, as well as you also collect your data from the register in a parallel form on a single clock pulse. So now this rotate right shift register or rotate left shift register is constructed like connecting your output terminal as again the input terminal. There is a feedback from your output to input. Here also output to input is connected. So in order to increase the number of states of your register, so let me prefer this rotate right shift register or rotate left shift registers, and these are used as a counters. Now, so in that we will move to your next topic, which is serial in our topic, which is serial in, serial of shift register of right shift. So in order to construct this shift register, we are going to prefer only the D flip flops. So you can use any type of flip flop, but they function like a data flip flop since our next state is exactly like your data input. So to obtain a serial in, serial out shift register, so it's a 4-bit shift register because I used 4 flip flops. So if we wanted to construct a n bit, so I have to use n number of flip flops. So how we have to connect this flip flops are in a cascading method using the cascading method. Cascading method is output of your first flip flop is connected as your data input to the second flip flop. Output of second flip flop is connected to third flip flop. Like this connection must be done till the nth stage. N minus 1th stage output must be connected as your nth stage input. So here only I have a 4-bit register. Hence, so here I have your 4 outputs. So output of first one is connected as data input to output of your second flip flop. Q2 is connected data input of your third, and output of your third flip flop is connected as data input to the fourth flip flop. And your actual serial output of single only one output terminal, one input terminal we have. So since it is a shift right, so serial input is connected on your extreme left hand, and the output is collected from your extreme right hand flip flop. So bit by bit you are going to load the register. For example, now initially let me reset your flip flop. So when you reset your flip flop, all the flip flop will be reset to logical 0. So for the 0 clock pulse, so upon clearing your contents, so QA or QA, QB, QC, QD all will give you the 0 outputs. So next upon giving the 1 input, so your clock is 1. So when clock is 1, so with this clock, so QA, QB, QC are loaded with the data of your whatever you are entering now. So now let I take an example. I wanted to load a data of 1011. So in this 1011 least significant bit is 1. So I will start with that. So 1 is loaded as a data input. So hence immediately on one clock pulse, first clock pulse, so the flip-flop 1 is changing its state from 0 to 1. Remaining will not change because the previous states are zeros. It will be continued. So next only the first flip-flop will be loaded with the new data which is 1. The second flip-flop, the output of your first flip-flop is connected as your input, and your first flip-flop is loaded with the new data input which is 1 in serial way. So next your third flip-flop, fourth flip-flop will give you the 0 outputs. Next on the third clock pulse, the third bit of your data input is transferred onto your first flip-flop. First flip-flop output is transferred to second flip-flop input. Second flip-flop input is transferred to third flip-flop input, and fourth flip-flop, third flip-flop output is transferred to the fourth flip-flop. Next, upon giving the fourth clock pulse, the last data input, which is the most significant data input, 1 is loaded onto your first flip-flop. So 0 is shifted to your second flip-flop, 1 is shifted to third flip-flop, and 1 is loaded, or it will output from your serial output terminal from your last flip-flop. So you can have your first data bit on a fourth clock pulse of your input. Now upon having this fourth clock pulse, you can obtain your first data output terminal. Upon your fifth clock pulse, you can obtain second data bit. Sixth clock pulse, you can obtain your third data bit, and seventh clock pulse, you obtain your last data bit. Like this, serially one by one bit is one after one. So you can get your output serially from your single output terminal in a serial. And now just by looking here, so the data is shifted one bit on a clock in the direction of your right board into your flip-flop, hence it comes under your shift right register. In the same manner, so we also have shift left register, where here one input terminal and one output terminal, common clock we are going to use, and that data input is connected on your right hand flip-flop, and your data output is connected on your left hand flip-flop. So on this your 4 clock pulses, your data is loaded into your all flip-flop. From the fourth clock pulse itself, you can obtain your serial data output from its output terminal of your shift left register. So the data is shifted from your right hand flip-flop to the left hand one by one. So it is transferred from QA to QB, QB to QC, and then QC to QD. So I connected here. The first flip-flop output is connected data input to the second flip-flop. Second flip-flop output is connected as a data input to third flip-flop. Third flip-flop output is connected to your as your data input to the fourth flip-flop. So based on your clocking, giving the input, so that same inputs are loaded into the flip-flop, and the data is shifted in the direction of one flip-flop to other flip-flop. Since you connected from right to left, so data is shifted one bit towards to the left. So hence it comes under your serial in, serial out, shift left register. Next, so let we move to your serial in, parallel out, shift register. In this serial in, parallel out, upon loading the register fully loaded, so then we can obtain your all the through this parallel output terminals. So you have multiple output terminals. So if it is an in bit, so n number of parallel output terminals are available. If it is a 4 bit, then 4 number of parallel output terminals are available here. Only one single serial input. So initially we will clear that, and upon giving the clock signal, and clear must be high. When clear is high and clock is 1, so then it accepts the serial data input, and so serially all the 4 flip-flops are loaded. Upon loading all the flip-flops are fully loaded, then you can obtain your parallel. Until that it is loaded, the register is loaded with all the 4 bits. So the outputs of which comes from your parallel outputs are invalid. So we will treat that as a invalid. So once it is loaded with all the 4 bits, so then only we can obtain your parallel outputs from your each flip-flop. In the same manner, we can also construct a parallel in serial out. So you can give the input to the register in a parallel way. So using a control input called shift or load. So this load can enable the new data to be accepted by the register, and if you are enabling your shift, then the data is shifted into your the flip flop towards to the right or towards to the left based on your data output terminal. So shift can provide you the data shift from one flip flop to other flip flop. Load, if it is enabled, so it can provide you loading your new data through your parallel inputs. So in order to load a new data through a parallel input, so this load bar must be equal to logic 1 and shift must be equal to 0. To shift your data from one flip flop to the other flip flop, shift must be equal to 1, load bar should be equal to 0. So to obtain that, so we are going to use some combinational circuit in addition with this flip flops. So here I used total 6 number of AND gates with 3 number of OR gates. Now each AND gate is having 2 inputs. So one comes from your parallel input. So all the even numbered AND gates are connected with the parallel inputs, and all the odd numbered gates are connected with the previous states of your output. So now when load bar is equal to 1, so that means so this shift is equal to 0. So load becomes 0, 0 bar is equal to 1. So this line belongs to load bar and this line belongs to shift. When shift is 0 and lower bar is equal to 1, the first line will be in active state, and the second line will be in an inactive state. When this first line is in active state, or it will give you logic 1. So output of this second NAND gate, even NAND gate AND gates, so second, fourth as well as your sixth AND gates depends on your data parallel inputs B1, B2, B3. Whereas with that, so these are enabled. So when these are enabled, for example, now I wanted to load a data of 1011 parallelly. So hence now what I'm going to do, so load bar I'll enable with logic 1 by transferring a logical 0 on your shift or load bar. So load bar become logic 1 and the first line will be activated with logic 1. So it will provide a path from your all the even numbered AND gates to your data inputs. So hence here B0 is directly connected to D0, B1 is connected through your AND gates 2 and your OR gate to the data input. B2 is connected through 4th AND gate and OR gate through your D2. P3 is connected through your 6th AND gate and through your AND gate to the data input 3. Like this you are going to enter your parallel data. So upon entering the parallel data or loading your register fully, then if you wanted to take out the data from your register serially, so we have to shift back your load control with the logical 0 and shift must be equal to 1. So this second line must be 1 and your first line now it becomes 0. So this 0 can disables your all the even AND gates and enables your odd numbered AND gates. When it enables your odd numbered AND gates, so here one of the input is connected to the second line which is shift. Now shift is equal to 1. So every AND gate one of the input is connected to shift. So hence it is 1. But the output of this AND gate depends on your previous states of your flip flop. So now as here B0 is 1, Q0 is 1 earlier and B1 is 0, Q1 is 0. So B2 is equal to 1. So Q2 is also equal to 1. So B3 is equal to 1. Q3 is also equal to 1. So Q3 is now it is equal to 1. So for the second clock, first clock pulse your data is loaded into this register. The second clock pulse, if you wanted to shift the data, then here you have to apply a load control with a 0. Shift must be equal to 1, which enables your first, and this Q0 is transferred, which is logic 1, into your second flip flop through the data input. So hence this one is transferred to the flip flop 2. Flip flop 2 output is transferred to the flip flop 3, which is 0, and flip-flop 3 output, which is Q2 is 1, so it's shifted onto the your fourth flip-flop, and Q3 will be outing from your register, which is the data bit of 1. So in order to exit the second data bit, so like this we have to shift your data using your clock signal. So every data bit will be allowed to your single output terminal. Upon your giving your next 3 clock pulses, we can have your all the data bits which you entered parallelly. So almost it requires 4 number of clock pulses to obtain your all the data bits. For entering your data, only 1 clock pulse is required. So in same manner, parallel shift register. In this parallel shift register, we're going to we don't have any cascading connection. So there is no connection between the flip flops. So you can enter the data parallelly and you can obtain your outputs from your each flip flop through your parallel outputs. So only one single clock is enough here. So to enter the data as well as to collect your data from your register, so which is known as your parallel shift register. So in next class we're going to learn about so what does mean by a bidirectional shift register as well as your universal shift register.